Okay, now we're going to discuss the biggest chapter of this course, which is about acid-base in aqueous solution. This is such a big section, and it usually takes us a month and a half to complete. And it's going to be divided into multiple parts. And the order is slightly different from that you have in the textbook. Okay, so I do want you to pay attention to the order. In the end, everything that's in the text will be discussed, but the order is slightly different. The first part of the section, I will only look at monoprotic acids and bases and their pHs, which is not going to include the autoionization of water in the equation. And this is part 1, which also is subdivided into 6 parts. And each part will be recorded separately. Now for the first part, and that is the introduction and the definitions of acid-base. At the end of this course, I just want to point out that this is the only table that you will actually really need. Okay, this table discusses strong and weak acids and their calculation of pH at different concentrations, and including or not including the autoionization of water. So by the end of this course, this is pretty much all you really need to have memorized, and then you could use it with other things. So with the introduction, we're going to look at what's an acid and what's a base. Well, if you ask my little daughter, she would tell you that usually an acid has a sour taste. Vinegar owes its taste to acetic acid, and citrus fruit contains citric acid. Now, a little bit of a higher level will tell you that these acids can corrode metals, and they react with certain metals to produce hydrogen gas. Anytime you put an acid, any type, on a metal, you will see that metal bubbling and fizzing. Even that metal, when you put them in water, because water can act as an acid, it will also produce hydrogen gas. Also, one of the biggest ways in order to tell if a compound is acidic or not is to use carbonate or bicarbonate. Put that, let's say, solid acid onto it, and you will see that it will also fizz because it produces carbon dioxide. Of course, we all know that acids produce protons and H pluses, which is we call a proton in this case, and hydronium ion, which is pretty much the same as H plus in water. Acids are electrolytes. They could be strong or weak. They react with bases to form a salt and water. Their pH is usually less than 7, and they turn a litmus paper from blue to red, or whatever color it starts with. It ends up being red if it is acidic. Some properties of bases. Actually, most soaps and detergents are made of bases, and they usually have a bitter, chalky taste. They're quite slippery, as soap is, and they produce OH minus ions in water. They're also electrolytes. They could be strong or weak. They react with acids to form salt and water. They have a pH greater than 7, and they turn the litmus paper to blue, whatever the color it starts with, it ends up being blue. Of course, we're not going to ask you about any of this because this is very basic. And here's a little bit of an introduction actually to our own body systems. And without the presence of an acid actually in our body, we cannot digest anything, any of the food. And the process of digestion starts from the saliva in the mouth, continues on from the upper stomach and to the lower stomach, and also continues into the intestine. And in different areas where digestion occurs, the pH actually varies. An average adult actually produces 2 to 3 liters of gastric juice per day. And the pH of this gastric juice is as low as 1.5. And this is actually sufficient to dissolve zinc metal. Imagine if I eat zinc, my stomach can dissolve it. Guess what? If corona enters and it enters into our system, my stomach can dissolve that coronavirus. The cells that line our stomach produces HCl, hydrochloric acid. And of course, these are ion channels, which brings the Cl in, or which brings the H plus in. And this HCl, the H plus of it, of course, it kills unwanted bacteria, and it helps to break down some of the foods. The concentration of this acid ranges between 0.01 and 0.1 molar. For some biochemical reactions, what happens in the stomach is this HCl converts, is required to digest the food because it actually converts something called pepsinogen. It's an inactive form of an enzyme. It converts it to the active form called pepsin, which can split the proteins in the food. Now, what do you need to know out of this? Actually, nothing. I just thought that it's interesting for you to know that about our own bodies. Of course, you've all experienced at some time where you have excess acid, and some acid from the stomach ends up being in the esophagus, and that results in a heartburn. It's also called acid reflux. As well, you also, if you have excess acid, when you grow older, you will start to actually experience some muscle contraction and some pains in your muscle. Even if you do some sit-ups, that actually produces lactic acid, and while you're doing your sit-ups, you experience pain that way. Now, the body, of course, can adjust itself with a buffer pH on its system, but you could also hurry it up and take some antacids or some antacids. Antacids are types of bases such as magnesium hydroxide, aluminum hydroxide, some calcium oxide. The biggest antacid is sodium bicarbonate. And the sodium bicarbonate ends up entering into the stomach. The carbonate ion gets converted and it picks up some of the excess acid in our stomach and throughout the lining of our esophagus, and converts it to another form of an acid, which then ends up becoming CO2 gas. So if you swallow some saliva which contains some bicarbonate ion, it's as if you're taking some antacid, and thus you help to neutralize the acid that you have entering into your esophagus. Of course, our blood, and you already know that the blood acidity is also constant at 7.4, and thus this blood is actually buffered. And we're going to talk about buffers and what they're made up of, and that's a new concept for you this year. Overall, the buffering system in our blood is made of hydrogen carbonate and carbonic acid. And you're going to see that hydrogen carbonate acts as a base, picking up any excess H in case there's excess protons in our blood, converting it to this carbonic acid, which then ends up being CO2, which then goes into exhaled into our lungs. And this is just a little slide here, which tells me that we have a bunch of things in our body from all tissues in the cell, all of them which require some acid-base interaction throughout, from the lining in our urine system, all the way to the cells in our lungs and into our blood. Up until here, I say you need to study absolutely nothing at all. Okay, now for the actual course. First thing you actually need to know is how do I recognize who's an acid and who's a base? And according to what definition is that recognition going to take place? There are 3 definitions for acids and bases. First, by Arrhenius, and he was the first scientist who defined them. And he said that acids, or an acid ionizes to release H+ in water. This fits into the idea that he has to have an H+ that is releasable, or that he can release inside of a water solution. So as long as he has an H+, he's in that category. And he said that bases dissociates, or a base dissociates to release OH- in water. And according to Arrhenius, and watch out for this, for him to release OH from Arrhenius' point of view, he has to have an OH. Okay, so once he dissociates, he automatically releases OH. Well, we're going to see where there's a flaw in this. Then came about Bronsted and Laurie, and Bronsted and Laurie said, well, an acid releases a proton, pretty much like Arrhenius, and he called it, it's a proton donor. And a base receives a proton, he called it a proton acceptor. And then came about Lewis, and we're going to see what the Lewis said, and he talked about more like acids are an electron pair acceptor, while bases are an electron pair donor. Now, just with those definitions, it's not always clear. So when an acid ionizes, according to Arrhenius, he has to have an ionizable hydrogen, a hydrogen that can be released or that gets ionized. Now, to get ionized and be released, it has to be pulled out by water. So you do actually need water to help this HCl become H+ and Cl-. Of course, you all know that this H+ actually doesn't exist well on its own. It exists as the hydronium H3O+. But there are some molecular acids which actually fit the Arrhenius definition. And they also have ionizable hydrogens. And here is that hydrogen, which is ionizable. And as well, you always need water in order to remove it. Hydrogens that are connected to the oxygen are the ones that are ionizable. So if you go back to the structure of this is acetic acid, these 3 hydrogens are connected to the carbon, and then you get a carbon that has C double bond O, O-, and this hydrogen is actually connected to that O-. Now, as for bases, according to Arrhenius, they produce OH- upon dissociation. And so in the cases where I have a solid dissolving in water, thus becoming NaOH aqueous in a solution of water, which then we already saw that can separate and dissociate, and then solvation can occur. This OH releases this NaOH releases OH-. As well, we can have calcium hydroxide. As long as this has hydroxide ion, it can release OH-. Now, there's no big problem with the Arrhenius definition. So why did we need another definition? We needed another definition because ammonia, which is well known as a good base, now it's not a strong one, but it's a pretty good base in water, it also can give up OH- when it reacts with water. So upon reaction with water, it does give up OH-. And so it releases OH-, but in itself, it doesn't dissociate to give me OH-. Look at him. He's NH3. I mean, I can't break him apart to become, to give OH-. Well, which gives us to the next definition, which is the better definition, which all the acid base fit in. This is the Bronsted acid base, which they said acid is a proton donor, base is a proton acceptor. And so to be a donor or an acceptor, so if an acid is capable of donating a proton, to donate something, it has to have someone who will accept. So he has to donate in the presence of a base where a base accepts that proton. And the base is capable of accepting a proton only in the presence of an acid who will donate one to him. So let's look here. If I have any acid HA, he needs to react with something that will accept this proton from the HA. So in this case, HA will be my acid, my X will be my base, and the X accepts that proton. The X then becomes HX, and then when it picks up this H plus, it becomes positively charged. And what's left over is, of course, A minus. Of course, HCl fits into this category, but now, according to the Bronsted acid, I have to put the water molecule there. Okay, now you're going to see throughout this course, I don't always include the water molecule, but if I'm following the Bronsted acid base definition, I have to include it. So this HCl aqueous, in the presence of water, becomes the water accepts the proton which the HCl donates. Okay, so HCl will donate a proton, the water accepts it, water becomes H3O plus, and unfortunately this becomes Cl minus, well left on its own without its proton. Let's look in the base side from a basic perspective. Let's say I started off with a base. To start off with a base, I either have a base which is negatively charged or a base which is neutral. Okay, so let's look at this A minus. If I start with a base that's negatively charged and he accepts a proton, again, I have to put this water in. Okay, so now water donates a proton to the A minus. Now this is H plus with A minus, so it becomes neutral HA. You don't have to put a charge on it anymore. And the water becomes HO minus or OH minus. Let's look in the case of a base which is neutral. Okay? It can also accept a proton as long as it, you're going to say, as long as it has two pairs of electrons, it can accept a proton. So here is a proton, a water, which is going to donate a proton to this base. And it becomes BH plus. Now, why does this take a plus? Because it was neutral and I gave it an H plus, so now it becomes BH plus. And of course, the water has become, it lost a proton, so it became HO minus. Why is this definition so important? Why is Bronsted-Lowry acid-base definition so important? Because suddenly now I can include ammonia in the form of a base. How so? Look at ammonia. It has two pairs of electrons. If I draw the Lewis structure here, there's two lone pairs there. And it's neutral. So here's my water. My water will donate a proton to the ammonia. The ammonia then becomes an H4. It picked up a proton, it accepted a proton, and I have to put a plus charge. Was neutral, it became positive. And of course the water became OH minus. Notice in all cases, OH minus is also released. So it also somehow fits into the Arrhenius definition, except he said that the material had to be dissociated to release. Here, the ammonia didn't dissociate to release OH, it reacted with water in an acid-base reaction to release OH. Which gives us to the next direct concept, and the concept of a donor-acceptor couple. In the Bronsted acid phenomena, you have to have a couple for the reaction to take place as an acid or a base. And let's look at this idea of the couple, okay, or the pair, the acid-base pair. So I just have this reaction, ammonia with water, becoming ammonium and OH minus. Okay? So here's my acid. It's actually water in this case. Well, we're going to talk about that water can be an acid or a base. So in this case, it's acting as an acid. The idea is, why is it acting as an acid? Because if you look at him, he starts off with water, and what did he become? He became an OH minus. So what happened to him? He lost a proton. Okay? So if he lost a proton, that means he gave up a proton, so he is the acid. He's the donor of the proton. What happened to the ammonia? Oh, it became ammonium. It picked up a proton. It accepted a proton. Okay, so in this type of reaction, the ammonia is acting as my base, and because it picked up a proton. Now, of course, if I didn't give you the products, unless you are aware that ammonia is acting as a base, you don't really know, because it has a proton. And who says that this proton cannot be, a donor? Actually, I can have an H2 minus, and this NH3 can become an H2 minus, which means it donated a proton, but not to water. It will donate it to something else. And so it's not always easy to recognize acids and bases, and it does come with practice. And that's why we'll show you some pKa tables and some tables to give you some practice on who's the acid and who's a base. Because the biggest thing in this course is, once you recognize if you have an acid or a base, that's a big thing. Now it's a lot easier if I just tell you this is an acid. All right, now, of course, we said that water is my acid. Now, in the end, he became OH minus. What we call this is, we call him a conjugate base. Now, why is this OH called a conjugate base? It's called a conjugate base because if I go in the reverse direction, look at what happens to him in the reverse direction. If you go in the reverse direction, this OH now, OH minus, picks up a proton from the ammonium so that he's acting more as a base in the reverse direction to become water. And our base, ammonia, has become ammonium, which is my conjugate acid. And again, why is it called an acid or a conjugate acid? Because in the reverse direction, it's acting as the acid. It will give up its proton to OH minus. And in all the phenomena of Bronsted Lowry definition, you always have to have a base with its conjugate acid and an acid with its conjugate base. Okay, and we call this a couple. The way we write up couples is we always write the donor and then the acceptor. Okay, so in this case, according to the Bronsted definition, who's the donor? In this case, we put the ammonium, and the ammonia will be the acceptor. So donor, acceptor. And here, water is the donor, becoming OH minus. So you always put the acid and then followed by the base. Now, again, if you just look at the couple in itself, you could always recognize who's the acid and who's the base. The one that has more protons is the acid. Okay, the one that has less protons is your base. So you always put acid, base, and that's my couple. Okay? And of course, they have to be, everything else is the same. The only difference between them is that proton. So you always have a couple or a conjugate acid-base pair. And we already decided, we said that the conjugate base, whatever comes out after an acid loses its proton, and a conjugate acid is the molecule that's formed after a base accepts a proton. So the conjugate acid is if the base is B, the conjugate acid will be HB. And when you write down the pair, you always put the acid followed by the base. Okay, look at this table. I want you to go through this table yourself, okay, and pick up a form, let's say H3O plus. Take this form, H3O plus, and say, what's the basic form of it? If I have to get the base of the H3O plus, I remove a hydrogen plus, and that means it becomes water. The couple now will be H3O plus H2O. Let's say I started with this, the acetate ion, and I ask you that this is the basic form, it's in the negative charge, and I want the acidic form. If you want the acidic form, you have to add a proton to it. So you add a proton, H plus, it becomes neutral, and you get the acetic acid. And then if you want to write the couple, it becomes the acid followed by the conjugate of it, or the loss of the proton of it. So you move the proton. Continue with these and make sure that for each case you can put any of the acidic form or the basic form in either of the two, and you can write down the couple. Just as an example, now that my hand is right here, look at this, HSO4 minus. If I told you that this is the acidic form and I want its basic form, what you would do is, if this is the acidic form, it's going to lose a proton to become SO4. It lost its proton. And now if it was a minus charge and it lost an H plus, it became a -2 because you lost an H plus. You lost a proton. So it becomes more negative. Okay, and so you put the acidic followed by the basic in the form of a couple. Okay, continue on with these and make sure you know how to write acid-base couples. The last definition is called the Lewis acid-base definition. And why was this actually needed? It was needed because there are some forms of the acid that actually did not fit in neither the Arrhenius nor the Bronsted. And what are those? Those are the acids that do not have an H plus, neither to donate nor to ionize. Example of such acids are the BF3. And you're going to see that in organic chemistry actually use BF3 quite a bit, especially in organic synthesis later on in life for you guys. But BF3 is called a Lewis acid. Now, what stands out with the Lewis acid, it's as long as it's a substance that it can accept a lone pair or a pair of electrons, and it has a vacancy, then, it's considered a Lewis acid. So look at this. It's a sextet, all right? There's only 6. It doesn't follow the octet rule, the BF3. So it doesn't have a full octet. So there's an empty valence orbital there, okay? And it can accept 2 pairs of electrons from anything that has 2 pairs of electrons. An example is ammonia. So in this case, ammonia is acting as my base. It's going to donate 2 pairs of electrons. And always in the Lewis acid base, you don't have a conjugate form. You always have an adduct that is formed. It's always a combination of the two. They add together. Actually, this should be a BF. This should now have a minus charge, and the ammonia now has 4 bonds, so it should have a plus charge in the adduct form. Okay, so here there's no protons donated or accepted. It's electron motion that's taking place. Now, I can look from a Lewis perspective. I can always see an H plus as something that has a vacancy. It doesn't have a full octet. Well, actually, in this case, it doesn't have 2 pairs of electrons. And water as my Lewis base. Look at this type of an adduct. This donates to this vacant H plus, a pair of electrons, and you get an adduct H3O plus. And so actually this acts as a base and an acid, if you will. What about ammonia with H plus as well? H plus is acting as a Lewis acid, right? H plus is actually quite a good Lewis acid, and the ammonia donates an electron to this vacant H plus. Now you all know that H plus doesn't actually exist in solution as H plus, but nonetheless, this is the idea of an acid, a Lewis acid base adduct that is formed. Throughout this course, we are going to concentrate on the Bronsted, okay? So we're always going to have a conjugate acid-base pair. Now, sometimes you see me just dissociating an HCl, but in a sense, we're only going to concentrate on the Lewis, okay?